Hello and welcome to Bay College's Intermediate Algebra online lecture series. These notes correspond to section 1.7. 1.7 notes or lecture is actually going to be broken into 3 separate videos. This is going to be video 1 where we deal with intersections. So we're defining intersections here, and the first thing we're going to do is we're going to consider 2 sets of numbers. The first set of numbers, A, is going to be 1, 2, 3, 4. And the second set of numbers, B, is going to be 2, 4, 6, 8. Now, this illustration shows the set in A, which is 1, 2, 3, 4, and the set in B, which is 2, 4, 6, 8. Now, what an intersection is asking us is what is in the values of A and B, what is in both sets? It's saying, what do they have in common? So what we have to do is just look at it and say, well, the numbers that are in both sets that they have in common is 2 and 4. So what's in A and in B? Let me just grab my chalk here, which I forgot to do. So an intersection says what they have in common, and we use a symbol in math that indicates an intersection. And that's this symbol right here, because we're looking for what do the two have in common? What's in both sets? We also call this an AND statement. And I'm just going to write AND here because this is going to be an important concept when we move into some example problems, because we're going to see how intersections work with inequality equations, linear inequalities. So this is an AND statement. What is in A and in B at the same time? It is the set of numbers 2 and 4. 2 and 4 are both in A and in B. And that's why we call it an AND statement. This symbol is an intersection. It means AND. What's in A and B? And we can see from our illustration it's 2 and 4. So now we're going to see how intersections apply to linear inequalities. And hopefully we remember what these signs mean. This is our less than, this is our greater than, our less than and equal to, or our greater than and equal to. So this symbol could be interchanged with any of these 4 here. The first thing we're going to look at is an example of set notation. This says x such that x is greater than -6. Well, the notation isn't the important part. The important part of is this statement here. X is greater than -6. This is also called algebraic notation. So if x is greater than -6, well, let's see what that looks like on our number line. Well, if this value here is -6, and x is greater than -6, it's saying any value to the right of -6. Now, there's 2 different ways to graph it. You could use an open circle, but I prefer to use a parenthesis. This means it does not include the value, but it starts at this value and any value to the right. So this is our graph of this statement. Now, if we want to write it in interval notation, because there are 3 ways to represent this quantity here, -6 to infinity, because the number line continues on for infinity. And you notice I use the parenthesis in interval, and that's why I prefer to use it here. We could use an open circle and then an arrow to the right. The open circle indicates this value is not included. If it had been an equal to symbol here, we could use a closed circle or a bracket. And we'll see some examples later that incorporate one or the other. Now, if we look at our next example, we have x such that x is less than 1. And if we graph that, well, let's say 1 is over here. Well, x is less than 1. That means it lies to the left of it on our number line. So again, it does not equal. So I'm going to use a parenthesis. And I'm going to draw an arrow to indicate any value to the left. If we want to write that in interval notation, well, to the left goes all the way to -infinity, up to 1, but not including it. So that's our interval. And that's why I prefer to use parentheses over the open circles, because I can just look at this and say, hey, at 1 is my parenthesis. It helps me write interval notation. So I get into the habit of using parentheses or brackets, and we can just translate that from the graph to our interval notation. Now, how does this relate with intersections? Well, what if I wanted to combine these 2? What if I wanted to say, what are the values of x that make both of these statements true? Well, in set notation, we can write a double inequality, and we'll talk about those in a moment. On the left side, we have -6, which is less than x. Essentially, I just took this value, and if I could lift it off the board and turn it around, look at it from the other side, it would look just like this. -6 is actually less than x because x is greater than -6. It just depends on the way you read it. And I want to combine it with this. X must also be less than 1 because we want to find out what is true for both of these. And here you can see it's just recopying it. I don't have to flip it around. Because our number line goes from least to greatest, I write my double inequalities as least to greatest as well. We need that consistency. So if we can do that here, that means we can also do it on our graph. I'm going to combine these two to see what they have in common. Where do their two graphs overlap? What are the solutions that make both of these statements true? Well, if we graph this one, we had a parenthesis here going to the right. And this one, we had a parenthesis going to the left. And even though these arrows do continue on for forever, essentially, we're looking what is common to both of them, this area in between. So if I can look at this, and now I'm ready to write my interval notation. If we go right over here, I have a parenthesis at -6 and a parenthesis at 1. This is my intersection in the interval notation. So we can represent it as a double inequality. We can represent it as a graph. And we can write it as interval notation. And we should be somewhat familiar with all these representations, as we will be asked to write our answer in different representations in our classes. Now, we're going to take a look at that double inequality. This is a special case that only applies a true inequality of an intersection. And we're going to look at some examples and say, well, what's wrong with this? Why is it not proper compound inequality format or double inequality format here? So we're going to look at this. Excuse me. If we look at our number line from left to right, smaller value here, larger value there, that's how we want to write it. That would be proper notation. But somewhere in here is not a true statement. So what we want to do is let's cover this up for a moment and say, is it a true statement if I take x out of there? Is -3 greater than 4? Well, obviously not, because negative numbers are always less than positive numbers. So this alone is not a true statement. If I do that, oh, now it's a true statement. But if any part of this is not true, then we have to exclude the whole thing. So this isn't even a true statement. It's not a proper double inequality. Now, if we look at the next one, if we can look at this, we have -2 and -3. Again, -2 is a larger number than -3. So it doesn't go from least to greatest, right? This one's more negative. But does it make a true statement? Well, it's not in the right format, and it doesn't make a true statement. This is wrong no matter how we look at it. -2 is not less than -3. It's greater than, and same thing there. So this is not a true double inequality. So we always want to check it. It must always be a true statement. Now, if we look at this last example here of a double inequality, -4 is greater than or equal to x is greater than or equal to -6. Well, again, just like the last one, it's not in the proper format from smallest to greatest number, but it is a true statement. If I cover up this portion here, -4 is greater than or equal to -6. -4 is greater than or equal to -6. So it is a true statement. And if you recall, in the last example, I said if we could pull it off the board and turn it around, well, I can do that here. If I can pull it off the board and look at it from the other side, just turn it around. We'd have the -6 over here. And by flipping it around, that's going to change the direction of my symbols. And I essentially have -6 is less than or equal to x is less than or equal to -4. And it does go from least to greatest. And these are less than, or in this case, less than or equal to symbols. This is proper double inequality. So this is how we want to write our intersections if we're asked to do so in set notation or algebraic notation. This is how we're going to write them. You're always going to have less than symbols, and it must be from least to greatest. All right, now let's go to an example here. we have x plus 1 is less than 4, and this is the key word here, negative 2x plus 1 less than 3. What this and tells me is it says go looking for an intersection. Find the values that are in both sets. So we're looking for the intersection. I'm just going to use my properties of inequality. I'm going to isolate x by subtracting 1 from both sides. X is less than 3. By subtracting 1, 4 minus 1 is 3. So we have this statement, x is less than 3. And we want to go looking here. I'm going to use my properties of equalities to solve this. I'm going to subtract 1 from both sides. Now I have to isolate this x by dividing. Now this is a common place where we make a small error, but we're all victims of those. Even your instructors make errors, it's true. If I divide by a negative, this is how inequalities are different than equalities. If I divide by a negative, because I want to isolate that x and undo this multiplication with its reciprocal operation of division, what's going to happen here? Well, if we fundamentally think about it, I started out with a negative value. Through some process of multiplication or division, I'm changing its sign. It started out negative, but a negative divided by a negative is a positive. So it went from being a negative to a positive. We had a sign change. Here we had a positive, but we divided it by a negative. Positive divided by a negative is a negative. Now this is what I tell my students. When you multiply or divide an inequality by a negative, you're changing signs. Be consistent. If you change the signs, you better change the sign. Okay, so x is greater than negative 1, because essentially by changing that negative, we're flipping it. We did a reciprocal operation by a negative, so we're changing signs. Be consistent and change that sign. So now we have x plus 3 and x less than 3, and x is greater than negative 1. Well, let's put these on a number line, because maybe our instructor is going to ask us to graph the compound inequality. So negative 1 and 3 are my values from left to right. And x has to be greater than negative 1, so that's any value to the right. And x is less than 3, but not equal. That's any value to the left. And we can see here we have this intersection where they have common values that make both statements true. It's true in this one and true in that one. So now we can write graph notation if we need to. And that would be a parenthesis here at negative 1 and a parenthesis here at 3. Any value in here makes this a true statement. So I can go ahead and maybe pick a test point just to be sure. I always want to check my work. And I know the value 0 lies in here. It better make both of these true, this one and this one. So 0 is less than 3. I know that's a true statement. 0 is greater than negative 1. 0 is greater than any negative number. So that's good. It's true in both statements. Now, the last thing I can do is write it in set notation. We have part of the set here and part of the set here. Let's write this as a double inequality, because we have shown that it is a true intersection. So I can say, well, there's negative 1 here, positive 3 there, again, left to right. And negative 1 is less than x. If x is greater than negative 1, if we could pull that off the board and turn it around, we'd see negative 1 is less than x. And that's what we have here. And x is less than 3. That is what it is. X is less than 3. And we can see this is a proper double inequality. Negative 1 is less than 3. So that's a true statement there. They're both less than signs, and it goes from least to greatest. All right, so that's that example. We're going to move on to this one here. What if we already have a double inequality? It's just not simplified. Well, we can use the same properties we used here. We use the properties of equality. What we do to one side, we do to the other. The only difference is this actually has 3 sides, 1, 2, and 3. So what we want to do is what we do to one side, we do to all the sides. So I see here I want to isolate the term containing the x and then eventually get x by itself. But I can do that by subtracting 9 to begin with. What I do to one side, I do to all sides. So I've got to remember to do it over here on the left side as well. 0 minus 9 is negative 9, is less than negative 5x, is less than 29 minus 9 equals 20. And now we have to divide by negative 5. My goal is to get x by itself. Well, I'm about to divide by negative, so when I do divide by a negative 5, it went from being a negative to a positive value of x. When I divide this by negative 5 and this by negative 5, this is a negative. Well, negative 9 over negative 5 is a positive 9/5. We had a sign change. 20 divided by negative 5 is negative 4. Now, because I had these sign changes, I have to be consistent and remember to change the sign. Now, is this in proper double inequality notation? No, because this value, a positive value, is on the left side and a negative value on the right. We want it from least to greatest. So again, I'm going to pull this off the board and flip it around. And when I do that, I flip the whole thing around. And we want to check to make sure it's proper and true. Negative 4 is less than 9/5, so it does go from least to greatest. These are less than signs. And negative 4 is less than x is less than 9/5. Now, if I wanted to graph it, I could do that as well, and I'll graph it right here. If this is negative 4, somewhere over here is 9/5. And we know that because it's less than symbols, we're just not including the values. We're using parentheses. And we can write it in interval notation now that we have it graphed. A parenthesis at negative 4 and a parenthesis at 9/5. So we have our algebraic set notation. We have our graphic illustration, and we have our interval notation. And this is how we apply intersections to linear inequalities, or inequalities in one variable. In the next video, in 1.7, we're going to look at how unions apply to different inequalities in that aspect. Thank you.